Chapter 14, Section 2 is on double integrals and volume. Our objectives are to use a double integral to represent the volume of a solid region, use the properties of double integrals, and evaluate a double integral as an iterated integral. Double integrals and volume of a solid region. Our goal is to find the volume of a solid region lying between the surface given by z equals a function of x and y and the xy plane. One way to estimate the volume of a solid region is by slicing it into these rectangular prisms where they kind of look like French fries. You can find the volume of each of those individual fries, if you will, by finding the area of the base times the height. Now, if you slice this a little bit in the x direction, we can call that a differential x, and slice that a little bit in the y direction, we can call that a differential y, and then the height of that French fry is the function of x and y. So it's going to be the area of the base, it's like your dy times your dx times the height of the solid region. And if you add up all of those little French fries, you can approximate the volume of the solid region. And by using the limiting process, making those French fries smaller and smaller and smaller, in other words, we're going to be setting up a iterated integral that will allow us to find the volume of a solid region. This slide shows the definition of a double integral. If f is defined on a closed bounded region R in the xy plane, and the double integral of f over r is given by this double integral where r, this is a new notation here, r is the base region of some function of x and y differential area, dA. dA is the area, the differential area of the base, which we're going to start off with dy times dx or dx times dy. And that is equal to the limit if you make those little changes go to 0 and adding up the areas of those rectangular prisms. We say that this iterated integral is that limit process, if the limit exists. The volume of a solid region then is, say you have this function f is integrable over a plane region, and then that region is R, then the volume of the solid region that lies above R and below the graph is defined as this double integral. V is for volume. This double integral where you see that R, oops, we see that R there, that is your base region, and you would determine the bounds of the integrals by looking at that region. And then your function f of xy and your differential area, that's going to be dy times dx or dx times dy. Evaluation of double integrals. Consider the solid region bounded by the plane z equals f of xy equals 2 minus x minus 2y. We've sketched planes in chapter 11, sketched them by graphing the intercepts, and we want to find the volume of this solid region that's bounded by the plane and the 3 coordinate planes. So we can set up a double integral for volume where R is the base region. That R would be the region in the xy plane. And the way you determine the bounds of that is by sketching it in 2 dimensions. It would be the integral where x would go from 0 to 2, and y would go from 0 to this line here where the plane crosses through the xy plane. And to find out where that crosses the xy plane, you're going to set that equal to 0, and you solve that for y. And that's how you get that upper bound. Now the height of this is the actual function f of xy, so that's what's inside your integral, and the order for your differentials is dy dx. Okay, here's another example, evaluating a double integral as an iterated integral. Here we want to evaluate R, the double integral where R is the region given by the inequalities of this function here. Now this this expression here, 1 minus a half x squared minus a half y squared, that could represent the surface in space, and then you want to set up this double integral that would give you the volume bounded by the xy plane and that surface within that region R. Now the region R is given by inequalities where x is between 0 and 1 and y is between 0 and 1. So you can sketch that base region in 2 dimensions. So your lower bound is x equals 0, your upper bound is x equals 1, or your left x equals 0, your right x equals 1, your lower y equals 0, and your upper y equals 1. So you have this square region, and we have this vertical representative rectangle. And when it's a vertical representative rectangle, the order of the differentials is dy dx. That little part here is dx. That's going to be on the outside. That larger dimension of the rectangle is your dy. And then you can see the bounds of integration. And then when you work this out, you'll find that the volume of the solid region is 2/3. Okay, so again, we replace this notation here, this double integral with an R, with the bounds that are given by the base region. Okay, first you want to integrate the inside with respect to y. Treat y as a variable and x as a constant. So we're treating all of this as a constant here. The antiderivative of this constant is this constant times y. And the antiderivative of a half y squared is y to the third, divide by 3 to get y to the third over 6. And now you have a single integral. You evaluate the upper bound. You're going to replace y with 1, and then you're going to replace y with 0 and simplify to simplify into a single integral. Now you have a single integral. You can integrate each of these with respect to x. So the antiderivative of 5 over 6 is 5 over 6x minus the antiderivative of a half x squared is minus x cubed over 6. And you then evaluate the bounds from 0 to 1, plug in the upper bound and the lower bound, and simplify. And you'll get 2/3. Okay, in the next few videos, I'll be going over some examples of evaluating iterated integrals for volume, where we could sketch the region and set up and evaluate the integrals. Now you can pause the video, you can try this one on your own, and then come back and check your work. Okay, so here we're given the double integral R. R is the base region, and we're going to use the inequalities here to determine the bounds of integration. I always like to sketch the region. X is between 0 and 2, and y is between 0 and 3. So x equals 0 is your left x. X equals positive 2, that's your right x. Y equals 0, and then y equals 3. Y equals 0 is your lower bound or lower, and then your upper is y equals 3. So you see in this case we get this rectangular region. The rectangular regions are always vertically and horizontally simple, so you can really choose whichever order of differentials you want here. And it's often you want to take a look at the integral itself to see what would be easier. If the order of the differential was dy dx, you treat y as a variable first. If the order of the differentials was dx dy, then you treat x as a variable first. So let's suppose we start this using a vertical rectangle. That little change here is your dx, that big change here is your dy. So when you draw it this way, the order of the differentials is going to be dy dx. Your bounds, your lower bound for y would be the bottom of that rectangle, would be y equals 0. Your upper bound for y, the upper portion of that box, is y equals 3. And then your left, if you slide that rectangle all the way to the left, that left x is equal to 0. Slide it all the way to the right, that right x is equal to 2. So these are going to be your bounds of integration. And let's go ahead and set it up. The double integral of y times e to the x plus y squared. The differential area. Now, dA here, just want to take a moment here, is the area of this representative rectangle. It's a differential area. And you can think of this as area of the rectangle as a length times a width. Always the longest side first. So your differential area is going to be dy times dx. So you're actually replacing the differential area with the differentials dy dx. So our inside bounds are going to be for y, where y goes from 0 to 3. I'm looking right there. And then your outside bounds are for x, where x goes from 0 to 2. Now we can begin by evaluating the inside integral. When you integrate this with respect to y, you're going to treat the y as a variable and the x as a constant. So in order to do this, we do want to use u substitution here. If you're using u substitution, you would let u equal that exponent, x plus y squared. Then your du would have to be, pause here for a second, so you just want to clarify that when you're evaluating the inside integral, you're treating y as a variable and x as a constant. Do that the same when you're using u substitution. Treat x as a constant, y as a variable. That du would then have to be 2y dy. So we do have the y and the dy. We have the y and the dy. The only thing we're missing is the 2. So we can put a 2 here as long as we put a 1/2 out in front. Also, we can adjust the bounds of integration. Our original lower bound for y was y equals 0. So if you plug in y equals 0 into this u substitution, then u equals x. That's going to be your new lower bound. And then your upper bound was y equals 3. So your u upper bound would have to be x plus 3 squared, or x plus 9. All right, that is going to be your new bounds when you do the u substitution. So it's going to be 1/2 the integral from 0 to 2 of all of that. And we're going to use u substitution here. And this is going to look like the integral of e to the u, and then the 2y and the dy make up your du. And then your bounds for u, this was y equals 0, then u is equal to x. And then when y is equal to 3, u is equal to x plus 9. Now we're going to integrate this. The antiderivative of e to the u du is e to the u. So it's going to be e to the u evaluated from u is equal to x to u is equal to x plus 9, and then dx. Now we have the integral. 1/2 the integral from 0 to 2. We plug in the upper bound is e to the x plus 9 minus e to the x dx. Now we have a single iterated integral. I'm sorry, we have a single integral now. We can evaluate this with respect to x. That's going to be 1/2 the antiderivative of e to the x plus 9 is e to the x plus 9, and then the antiderivative of e to the x is going to be minus e to the x, and we evaluate that from 0 to 2. Let's plug in the upper bound, and we get 1/2 of, plug in the upper bound, we get e to the 2 plus 9, e to the 11th, minus e to the 2nd power, minus what you get when you plug in 0. You plug in 0, you get e to the 9th power, minus e to the 0 power, which is going to be 1. Okay, so this would be your exact answer. You can simplify or get a decimal approximation, but that would be your final answer when you're evaluating this double integral. The key in doing this was using the region to determine the bounds of integration and then working through the problem.